If I draw a force versus time graph, there should be three words that immediately come to your mind. What are those three words that we should think of every single time? Good. Area equals impulse. Regardless of what the shape of this graph is, regardless of whether we're even able to find the area of this graph. Maybe it's a shape like this, and we're not even able to find it because of the odd curve at the top. It doesn't matter. I still want you to think those three words, area equals impulse. We always think that. Now, what else are we sometimes going to think depending upon what we're asked to solve for? Always area equals impulse. Sometimes an equation that goes along with that. What is that equation? Cody? Good, m delta v. Be careful you don't say m times v. That's momentum. And sometimes you'll get away with that. It's not mv, though. It's m delta v. If you say mv, you'll sometimes get away with it. If you say m delta v, you'll always get away with it because you're doing it correctly. Now, what other equation can I not use in conjunction with this? Yep, good. Delta P is equal to F times delta T, and that's technically correct. The problem is, if we have a graph that's force versus time, odds are we're not going to know what force to use there. Technically, it's the average force. We don't know what the average force is there, so let's just avoid using that equation entirely. This one we'll always use. This one we'll sometimes use, depending upon what we're asked to solve for. All right, what if we have a graph that goes below the x-axis a little bit right here? Calculate this area right here. That's going to be a triangle, right? That's going to be found by 1/2 base times height. Rectangle, base times height. Triangle, 1/2 base times height. What do all three of those shapes have in common? What do all three of those areas have in common? Despite the fact that two of them are triangles, one of them is a rectangle. What do they all have in common, Jessica? Good, they're positive. It's a positive area, therefore a positive impulse and momentum gained. Versus this area down here. Be careful, a lot of people will try to find this area. Hey, that's not what we want. We want this area right here. That's going to be found by 1/2 base times height as well. What's different about the red triangle versus one of the green triangles or the green rectangle? Good, that's a negative area, which makes it a negative impulse, which means it's a loss of momentum or a momentum to the south or the opposite direction. Make sense? All right, good. Somebody during period 2 asked me a really good question today. If we have the impulse and say let me just draw a picture of this actually. Let's say we have a force and we have a time here. Force is in newtons, and the time is in seconds. And we get a graph that looks like this. Let's say this is 0.1 seconds, and this down here is going to be 0.3 seconds. We don't know what's on the y-axis of this graph here. Let's say we knew what the impulse was. If we knew what the impulse was, okay, let's say we've got this. Could we use this equation to solve for the force? Could we then use this equation? Although I've told you, never use this equation. Is this a situation where we could get away with it? It isn't. It still isn't. This force is the average force. What's this force right up here? That's not the average force. That's the maximum force. Let's solve for this, okay? Let's figure out what that maximum force is. You need to be given a little bit more information first. So let's say the mass of this object is 2 kilograms. Let's say the initial velocity of this object is 0 meters per second. And let's say the final velocity of this object is 10 meters per second. And we want to find this value of maximum force right there. How would we go about doing that? There is 28 of you in this class. 28 people in this class. 28 out of 28 of you should know where to start. Every single person should know where to start. You might not be able to solve this question. You might not be able to get an answer. I can accept that. But everybody knows where to start. Where do you start when you see a force versus time graph? Area equals impulse. Now, we can't actually find the area here because although we have the base, we don't know what the height is, right? But we're still thinking that. We always think that, regardless of what we're asked to solve for, area equals impulse. You're going to find that that becomes important in a couple of minutes here. What's the second thing that we sometimes do? We always think this. We sometimes think delta P is equal to m times delta V. Well, look at this. Usually, we find the impulse by finding the area and then set it equal to m times delta V. This time, we can't find the area, but we do know mass and delta V. So we can find the impulse that way. 2.00 kilograms times 10 minus 0 gives me an impulse of 20 Newton seconds. That makes sense? I got an impulse of 20 Newton seconds. But wait, the area equals the impulse. In the area of this, which is 20, because we just found the impulse and the area is equal to the impulse, is equal to 1/2 base times height. And the base of this is 0.3. Let's find the height. 20 times 2 is 40. 40 divided by 0.3 is 133. So the height of this is about 133. What units? Yeah, Josh? Newtons. Yeah, it's 133 newtons. The height of this triangle is in newtons because what's on the y-axis? Newtons. What if we just found the height of this triangle is the max force? We've just found the max force. You see what we've done there? We started off the way we always start off. Area equals the impulse. It didn't matter what we're asked to solve for. It didn't matter that we weren't even able to find the area first. We started off that way because we know that we're eventually going to come back to that if we don't do it right away. We're eventually going to come back to that. Area equals impulse. So I couldn't do anything with that right away. All right, let's go to our second option, which is delta P is equal to m times delta V. I got something from that, and then I went back and did the whole area equals impulse thing. Does that make sense? That's a good question. That's a really good question. And that stemmed from, say, a question a student asked this morning. So moral of that story is, even though the answer to that student's question was wrong, or the student's question was a little bit misguided, it led to this, which is a really, really good question. So ask the question. Even if you end up being wrong, that's okay, because it sometimes leads to something like this that is a really good question. All right, we had 2 questions for homework on these force versus time graphs on page 462. Let's take a look at those 2 questions now. You want to go over one of these, both of these? Both of them? Okay. Question number 1 says, draw a graph of a net force as a function of time for a 0.650 kilogram basketball being shot. During the first 0.15 seconds, it increases from 0 to 22, and during the next 0.25, it decreases back down to 0. So let's draw the y-axis force. It's in newtons. The x-axis time, it's in seconds. The good news is at least we're in standard units here, right? A lot of times we're in kilonewtons or milliseconds or 10 to the minus 1 seconds. Let's say this is 0.15, 22 newtons. I go up from 0 to 22 newtons in 0.15 seconds. Then I go back down to 0 newtons in 0.25 seconds. What's this time going to be over here? 0.4, right? Because 0.25 and 0.15 is 0.4. So it's going to look like this, right? There's my sketch of a graph. Now, even though question B asked me to find the impulse, that's what I do anyways, right? Because area equals impulse, and that's the first 3 words that come to my mind. So I'm going to do that now. I'm going to say area equals impulse equals 1/2 base times height. Some of you may have broken that down into 2 triangles. How many people did that? Anybody break it down like this? That's okay if you did, by the way. It's just more work, that's all. You don't have to do that. You don't have to have a right-angled triangle to use the Pythagorean, or to use this equation. You do use the Pythagorean theorem, but not the area of a triangle equation. The base here is 0.4, and the height is 22. And when we multiply 1/2 times 0.4 times 22, we end up getting 4.4, and the units there would be Newton seconds. Good. All right, what's the speed of the ball when it leaves the shooter's hand? Well, it's my other equation now, right? M times delta V. Solve for delta V here. Delta P is 4.4. M is 0.650. It gives me 6.7, 6.8. The basketball started at rest, right? So if we've just solved for delta V is 6.8, then that's going to be the final as well because it started at rest. All right, let's take a look at number 2. A soccer player heads the ball with an average net force of 21 newtons west for 0.12 seconds. Draw a graph of the ball as a function of time and assume that F net is constant during the interaction. So here's my graph, F on the y-axis, T on the x-axis. Look what I'm going to do here. Watch what I'm going to do. I'm going to make this 21 newtons. I'm going to make this 0.12 seconds. Can anybody suggest to me maybe why I drew that below the x-axis? Why did I draw that line where I did as opposed to up above? Yeah, because it's west. Did anybody draw it below the x-axis? So everybody else drew it above the x-axis? Is it okay to draw it above? Sure it is. If you do what? If west is positive. Does that make sense? I'm sticking with west is negative because I almost always do that. Just stay in the habit of it, right? You can make west positive. You just got to be careful if you make west positive that you're consistent. And it's harder to be consistent because we're not used to doing that. I'm going to stick with this though. We're going to find the impulse provided to the ball. Impulse is the area of course, which is it's just a rectangle, so it's base times height. The base is 0.12, and for me, the height is negative 21. For you guys, the way that most of you guys did it, the height would be positive 21, right? But for me, negative is west. For you, positive is west. I get sorry, just calculated that wrong. 2.52. Now we want to find the mass of the ball. So we're going to say M is equal to delta P over delta V. Delta P is equal to M times delta V. Delta P, the impulse, is 2.52. And be careful with this. That should be negative, by the way. Be careful with this. Delta V for me is going to be negative 2 minus 4. If you did it making west positive, then your impulse should be positive 2.52, and your change in velocity should be 2 minus negative 4. Does that make sense? Either way you look at it, you're going to end up with an answer of 0.42 kilograms, and that's got to be positive. You end up getting a negative. You've messed up with the sign somewhere. Yep. Yep. No, it's okay. It's okay. It's okay if you don't. But just it's a good idea too, but it's more important for yourself than for anybody else. Like you need to know what something means. If you get an answer, you need to know what it means, right? On a test or on a quiz or on an exam, the 4 options might be 2.52 west, 2.52 east, whatever. You get a negative, you get a positive, whatever, as long as you know that means east or west. Okay. By rights, you probably should state it, but it's not the end of the world, as long as you know. Good there? All right, we had a number of multiple choice questions that I asked you to work on last night as well. Practice question sets 2A and 2B. All right, our multiple choice questions from practice questions 2A. We're going to go over all of these here, starting with question number 1. The physical quantity that can have the same unit as impulse is? That's going to be momentum, right? If impulse is the change in momentum, then it's going to have the same units of momentum, right? Next question. This is where it starts getting a little bit harder, these questions here. There's a scenario here with 4 questions here. It says airbags are designed to deploy when a car moving at a minimum speed of 18 kilometers per hour comes to a crashing stop. The impact sensor, also moving at 18, consists of a small steel ball at point of 0.050 kilograms, which is held in position by a magnet. It takes a thousandth of a second to break free, connects with 2 electrodes at the other end, completes a circuit. Just so you know here, just kind of beyond what we have to know here, but when it completes this circuit here, joins this electrode to this electrode, it applies an electric current through this powder that kickstarts a chemical reaction that produces a gas. And I'm not sure what the gas is, but it's not air. It's not air at all. Some other gas that is produced really, really, really quickly. So quickly that, in fact, that it inflates the airbag long before your head actually makes contact with the airbag. In fact, maybe you didn't know this, but there's holes around the outer edge of the airbag, all around the outer edge of the airbag. And there's holes around it so that the airbag is actually in the process of deflating by the time your head ever actually makes contact with it. So it inflates so quickly that it's inflated and is now deflating before your head ever hits it. Anybody explain to me, based on what we did yesterday, why that's important? Why we don't want to have it inflating when it hits you, but rather we want those holes around the outer edge so that it deflates? It would, but even when it's deflating, it still exerts a force on you. Done? It would be a greater force, yeah. Can anybody explain to me why it would be a greater force? Yes, and this is what we were talking about yesterday, right? When it's deflating, it increases the stopping time. Hey, if it's inflating, it's probably better than your head hitting the steering wheel, but the stopping time is still pretty quick, so the force is still pretty big. But if it's deflating, it increases the stopping time even more, decreases the force even more. It's kind of like catching a baseball, right? Everybody knows intuitively when you go to catch a baseball, the ball's coming towards you, you're standing there, you don't do this. You don't move your glove towards the ball really, really quickly because it's going to bounce off, right? So what do? Kind of bring it back a little bit. I'm exaggerating here, right? Like not this much, but you still bring it back a little bit, right? Cradle it. Because when you're moving in the same direction as that ball, you increase the time that it takes the ball to stop. When the airbag is moving in the same direction as your head, it increases the time that it takes your head to stop. All right, so we want to find the magnitude of the force required to break away from the magnet here. We're going to say F times delta T is equal to M times delta V. We know it's impulse because it's force and time in the same question. Force ends up being M delta V over delta T. So we've got a mass here of 0.05, a change in velocity. 18 kilometers per hour is 5 meters per second. Divided by the time interval of 1 times 10 to the negative 3 seconds. And I think when we do that, I think it was C, wasn't it? 2.5 times 10 to the 2 newtons. Is that okay? At D? I think D's wrong. What'd you do? That exact thing. 3, if the car was moving at 18, how fast could the ball be moving after impact? Well, look, if car is moving at 18, car comes to a stop, and I am a passenger, I keep moving at 18, right? Well, so would the ball. So would this little metal ball keep moving at 18 kilometers per hour, which is 5 meters per second. An object in motion stays in motion at a straight line at a constant speed until acted upon by an unbalanced force. The car stops, but the ball keeps going. That's what allows it to go down to the other end, complete the circuit, and fire that airbag. 4, question real similar to number 2 with different data here. The car was initially moving at 18 kilometers per hour. Driver had a mass of 70. Airbag stopped him in 0.1 seconds. What's the magnitude of the force? F times delta T equals M times delta V. Mass 70, delta V is 0 minus 5, because we got to be in meters per second here, right? Divided by the time of 0.1. And I believe that one was 3,500. 3.5 times 10 to the 3. It would actually be negative, right? But what are we looking for here? The magnitude. So when you're looking for the magnitude, that doesn't mean you drop the signs all through the question. It just means you drop the sign at the end for your answer. And finally, number 5, this one bugs us. This one drove people crazy. Why did it drive people crazy? Because the easy ones often do drive people crazy. People overlook the obvious in the easy questions. Look, we got a passenger not wearing a seatbelt. How fast does the passenger go after the car stops? 18 kilometers an hour. You want to find out how far he goes? Well, he's going to move at 5 meters per second or 18 kilometers per hour for 3 times 10 to the negative 3 seconds. Done. That's it. Moves at a constant speed. Here's the speed. Here's the distance or displacement that he travels here. We could eliminate C and D right away. Okay, if you were struggling with this, you could eliminate C and D right away and guess from 2. How is it that you could eliminate D? Like, how do you know that D is wrong? Just by looking at it. Yeah? If you're not wearing a seatbelt and you keep going at a certain speed, your displacement can't be 0. No matter how short the time interval is, you must have a displacement, right? So it can't be 0. Now, how do we know that 5 is wrong? It's not realistic, right? Like, think about that. You're not wearing a seatbelt. You move forward during the time that the airbag is inflating. During the time that the airbag is inflating, you've moved forward 5 meters. So you're lying on the road, picking up pieces of yourself, looking back at the airbag. Oh, it's finally inflated. So that's not a very good airbag if you're on the road before the airbag ever inflates, right? Okay, so it can't be 5 meters. If I had to guess, A, B would have been 50-50. Okay, obviously I don't want to guess. I want to know how to do it. But if I got to guess, at least I got a 50% chance as opposed to a 25% chance. All right. We had a couple more questions on practice set number 2B. These were also impulse. First question involves a skier here. It says at the starting gate of a downhill ski race, the skier pushes with his arms and legs to get going as fast as possible. Skier leaves the gate with a speed of 1.6 meters per second. And then the skier goes down the hill. And there's a whole bunch of data with the skier going down the hill. I'm not going to worry about that so much because I'm looking for the magnitude of the impulse as the skier leaves the gate. As the skier leaves the gate, we know that his impulse is equal to F times T, but also M times delta V. His mass is 68.2 kilograms. And his delta V is what? Well, I said his final velocity as he leaves the gate is 1.6. And I said his initial velocity was 0. But doesn't it say here his initial speed is 1.6? So what's the deal there? Why am I going against what it says there? Yeah. Okay, yeah, that's the initial speed of the run down the hill. We got 2 problems here, right? We got the problem of him leaving the gate, and then the problem of him going down the hill. The initial speed of going down the hill is 1.6. That would be the final speed of leaving the gate, right? Presumably, the initial speed of the gate is 0, right? Because you don't usually see skiers taking a running start when they're going through the gate. Or a skiing start, I should say, I guess. We do the math on this one, and it works out, I believe, to be A. Is that right? 1.09 times 10 to the 2 Newton seconds. Good. Oh, this one. I forgot about this one. I was thinking we were almost done, but this is the toughest question of them all. All the ones we did today. So a full drive is full draw, I should say, is the maximum distance that an archer can pull back an arrow using the recurve boat shown below. A particular archer requires an average force of 130 newtons to pull a full draw of 70 centimeters. I'm going to circle this. I'm also going to circle this mass of the arrow, 20.6 grams. Okay, under control, I think we're pulling it back with a certain force, an average force of 130 newtons. We don't know what a time is. As soon as I saw that force, I started thinking impulse, but then on the other hand, it doesn't say time. So maybe not. We'll see. See what the question asks. The question says, what's the impulse? Okay, so I am going to do impulse. Impulse is F times T and M times delta V. We're looking for impulse. We have force and we have mass. In order to find impulse, we need either time, we need to get time so we can multiply it by force, or we need to get delta V so we can multiply it by mass. Got it? Now, you may be looking at this and say, I don't know how to get either one. That's okay. What you need to do is something that you can do. You don't have to necessarily know how you're going to get T or V. Just do something. We have in this question a force and a mass. That allows me to get the acceleration. Is it going to be helpful? You know what? Probably. Probably. But even if it isn't, don't worry about it. Get it, because on the chance that it may be helpful. My force here was 130 newtons. And my mass here was 20.6 grams or 0.0206 kilograms. We do the math there, solve for acceleration. It's a big number, a really big number. Just don't remember what it is. 130 divided by 0.0206. 6310. 0.6796. That is a big force, big acceleration, sorry. Okay. Well, that's not T or V. Anybody have a suggestion, though, how I might find one of those two things with A? Well, we can't use F equals MA because we just did that, right? If I use F equals MA, then I'm going to say this times this, and guess what I'm going to get? 130. Yep. Okay, VF squared is equal to VI squared, which is 0, plus 2AD. We know what A is now, 6310. D was 0.7, I think, wasn't it? 70 centimeters? Let me just double check that. Yeah, 70 centimeters. What do we got there? $93.994. Well, that's pretty fast. Well, that's the final velocity, but that's also the change in velocity because the initial is 0. Look at that. Now we got M and delta V. We can multiply these two together, and we get impulse, right? Good. Anybody do it that way? Anybody get the right answer by doing it that way? Good. Good. That's a tricky question. There is one more thing you could do, though. Once you have A, you could have used D is equal to VIT plus 1/2 AT squared. Oops. This disappears because VI is 0. We know what this is. We know what this is. Solve for T, and then plug that into there. Guess what you get when you do it this way? 1.94. Guess what you get when you do it this way? You better get 1.94. If you do it two different ways and both legitimate, then you better get the same answer. It's the kind of thing where sometimes we're a little bit pushed for time on an exam. If you have extra time, this is the way I always used to think when I was in school. If you have extra time, you go back and checking things. If you can think of another way to do something, do it. Do it the other way. Do it a different way. Right? Not the same way as you already did it. Because if you do it the same way, you're bound to make the same mistake as you made the first time, right? If you made a mistake. Do it the other way. But only if you have time, right? That's something you do at the end of the exam if you have leftover time. Josh? No, that's a good question though. Could we do this and say delta D over delta T? We could not, because if there's a change in velocity, that's inferring acceleration. And when there's acceleration, we can't use the equation that describes constant velocity. That make sense? So we'd have to use this or one of those acceleration equations that you learned in physics 20. Okay, good question. Yep. Yep. One last question here, and this goes back to what we did yesterday as well, right? A rock climber falls and is saved from injuries by climbing a rope that's slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of impulse, because the elasticity does what? Well, when this person falls and comes to a stop, his or her impulse is predetermined. What do we want to do usually? Increase the stopping time, decrease the force. The answer is going to be A.